In this video, we will look at proving the work energy theorem. The work energy theorem says that the total work done on a system, which you can also call the network, is equal to the change in kinetic energy of the system. To prove it, we start with the definition of work, which is simply the integral of force with respect to displacement, the dot product, from some initial position to some final position. Since we are interested in the network, we will look at the net force acting on the system. However, from Newton's second law, we know that the net force is, in most cases, simply equal to ma. So we've gone from a dot product of F net and dr to a dot product of ma and dr. M is just a scalar constant, so it can sit out front. In fact, we can pull it out of the integral if we need to. But acceleration is simply the rate of change of velocity. So it's dv over dt. The next step is the slightly dubious one. We simply shift the dt over so that we now have dv dotted with dr over dt. However, what is dr over dt? Well, this is simply the rate of change of position, but that's velocity. So we have converted our integral into the integral of m times dv dot v. So to summarize, we have shown that the network is the integral from some initial configuration to some final configuration of mv dot dv. The switch here is because a dot b is the same as b dot a. To evaluate this more simply, we will look at the 1D case, but the same ideas hold even in the 3D case. So in 1D, this integral becomes simply integral initial to final m vx times dvx. Right? So all the forces and velocities and displacements are all in one dimension. M is a constant, so we can pull it out. And what do we have? We have integral vx dvx, but that's like integral x dx. So the result is m, and then the result of the integral here is vx squared over 2, evaluated at final and initial points. To recap, we have shown in the 1D case that the network is equal to mass times vx squared over 2, evaluated at final and initial, but that is simply m vx final squared over 2 minus m vx initial squared over 2. But that is the difference in the kinetic energy. So we have shown in the 1D case that the work energy theorem is true. The network on a system is equal to the change in kinetic energy. Brief note, how would we do the 3D case? So there we would have integral v dot dv, but that is the same as integral vx dvx plus vy dvy, whoops, plus vz dvz, right? I'm just doing the dot product of the v vector and the dv vector. So I can split this up into 3 different integrals. all from initial to final. And each of them would turn into this v squared over 2 form. But vx squared plus vy squared plus vz squared is simply v squared. It's the magnitude of the v vector squared. So even in the 3D case, we get a similar result. And in fact, you can directly think of going from v dot dv, the integral, going to v dot v over 2. But v dot v is simply, again, v squared.